Hello everyone and welcome to this talk on vanishing spaces of random sets and applications. I am Siddharth Bhandari at Simons Institute and this is joint work with Prahlad Harsha and Ramprasad Saptarishi from TIFR Mumbai and Srikanth Srinivasan from Aarhus University. So let's dive straight in. We'll be studying a very basic question about the vector space F2 to the M, which is the M-dimensional vector space over F2. So say we throw k random points in F2 to the M, Z1, Z2 up to Zk, and they are distinct. And what we will be interested in analyzing is the behavior of the Reed-Muller MR family, which is our favorite family of codes, but formally we are interested in the space of multilinear polynomials in M variables of degree at most r. So these are just described in a little more set theoretic notation. So these are polynomials which consists of monomials of degree at most r. They are multilinear, so the individual degree in each variable is at most 1 and the field is f2, so the coefficients are either 0 or 1. And what we will analyze is the space of all degree r multilinear polynomials, so polynomials belonging to RMMR, which vanish at every location in S. So a bit more formally, this is what we want to analyze. Now, the question is, what can we say about the random variable which is dimension of this space? This is a random variable because S is a random set of points. One thing we can always say is that the dimension of this space IRS, which is what we are trying to analyze, is at least M choose less than equal to R minus K, which is the size of S. Why can we say that? Because if you think about it, the Reed-Muller MR family that we defined above really consists of M choose less than equal to R uh, monomials taking coefficients in F2. So its dimension is M choose less than equal to R, right? These are the number of monomials you can form in M variables of degree at most R. So the dimension of RMMR is M choose less than equal to R. And what we really say when we want PZ1 to be 0 is a linear equation in these in the coefficients of these monomials, right? So we are at most writing K linear equations. So the uh, dimension of IRS has to be at least M choose less than equal to R minus K, because it can't reduce by more than the number of equations we write. And what we show is that this maximal reduction of K is more or less what happens in case S is random. There is a bit of uh, a condition here on R. So we need R to be not uh, too large in comparison to M, or rather we need R to be lesser than gamma times M for a universal constant gamma. And then as K approaches M choose less than equal to R, or is just a little shy of M choose less than equal to R, which is the regime when this bound stays meaningful, because if K exceeds M choose less than equal to R, then this bound doesn't really make much sense. What we show is that you do get that maximal reduction in dimension with high probability, right? So we need R to be sufficiently small compared to M, but it's just like there is some universal constant, R needs to be less than gamma M, and as long as K is slightly shy of M choose less than equal to R, this maximal reduction happens with high probability. So now let's move on and come and applications. So Wei and Kivash and Sudakov did show something in case S was an arbitrary set of size K. So not a random set, but an arbitrary set. So kind of an adversarial choice here. And what they showed is that the dimension of IRS is upper bounded by M choose less than equal to R minus log K choose less than equal to R, right? So they are not getting the maximum possible reduction of size, which was of size K, but the reduction is only like log K choose less than equal to R, which is going to be less than K. So this is exactly what is the comparison. So in the worst case, the upper bound on the dimension is much larger than what happens for a random set, right? And The worst case example to see the tightness of this bound is actually not too difficult. So a subcube of size 2 to the L is the tight example. So let's consider a subcube in which the first m minus L coordinates are 0. So we can easily see here that IRS, that is the set of all polynomials that vanish on S and are of degree at most R. Uh, this is exactly the span of all monomials which involve at least one of the first m minus L variables. And the dimension is hence just m choose less than equal to R, which is the total number of monomials minus all those monomials which do not involve any of the first m minus L variables, which is L choose less than equal to R, which exactly matches the bound. So essentially in the random case you get a much more drastic reduction in the dimension, and this happens with high probability. So moving on to further prior work and applications, these bounds of Way and Kivash and Sudakov have found applications in numerous places, because I mean, it's a very natural question and you expect to deal with it every time you're trying to analyze polynomials over finite fields. So Ben Eliezer, Hood and Lovett used this bound to show that a random degree d plus 1 polynomial is not too correlated with any degree d polynomial. And Ni and Wang used these bounds to extend the Kakeya set theorem. And this thing which is of major concern to us, which are the Reed-Muller codes, which are going to be the star of our show, they also have a very intimate relation with the bounds that we were describing, and we will soon see why. But specifically, Abesh, Pilka, and Victorson use these bounds to show that Reed-Muller codes of really high rate, so RMMR, when R is just square root m shy of M, they achieve capacity over the binary erasure channel. And we will get into the nitty gritties of this very soon, but I just wanted to state the result out for a minute. And also very recently, Chen, Day and Vijay Raghavan provide a sub-exponential time algorithm to learn a hidden subspace from a mixture model. So with some probability, you are getting a sample from the hidden subspace, and with some probability, you are getting a sample from the ambient space, which is f2 to the m in our case. And they give a sub-exponential time algorithm in case the codimension of the hidden space is at least square root m. Okay, and naturally these applications actually need not necessarily have had used the worst case bounds. So because we had a new result which talked about the random case, we tried to see if we can find improvements, and we did in fact find improvements for some of them. I'm not sure what happens in the other cases, but for the specific case of Reed-Muller codes, we are able to show that they achieve capacity over the BEC channel even when R is m times 1 minus gamma for some universal constant gamma. So recall that earlier you needed R to be as large as m minus square root m. Now we are happy even if R is larger than m minus gamma m. So we extended the range of parameters in which the Reed-Muller codes achieve capacity over BEC, at least that we know of. And by standard reductions or results due to Abesh, Pilka, Vigderson, and Shabdashi, Pilka, and Vogue, this also implies capacity for the binary symmetric channel for a certain range of parameters. So sorry, that should have been an m comma m minus 2r, but it's okay. And in fact, the proof framework that I will present to you can be used to show that uh, there is a way to relate capacity over BEC with the weight distribution of the dual code, right? So in this case, the dual of the high rate code would be a low rate code, and that's what we actually analyze. And uh, it's an interesting connection, and this does not restrict itself to just Reed-Muller codes. It can be used for any linear code. And also using our randomized bounds, we are able to extend the range of parameters till which the Chen Telcode Vijay result works. And earlier they needed the codimension of the hidden subspace to be omega square root m. Now we are happy with any super constant. So moving on to the matrix view and of this question and its connection to the binary erasure channel for Reed-Muller codes. Uh, let's sort of refresh what Reed-Muller codes are. Of course, they are our favorite codes in coding theory. The message space of these codes is the space of all multilinear polynomials in m variables of a prescribed degree bound, in this case m minus r minus 1, and the encoding of a message polynomial p is simply obtained by evaluating p at all locations in f2 to the m. And what we'll be really using for our proof is the parity check view of this code. And we'll denote the parity check matrix with this notation EMR. For introducing the parity check matrix, I just wanted to introduce some notation. So we denote the set of all degree at most r monomials, which are going to be sort of like the basis vectors of the dual space of Reed-Muller m minus r minus 1 by this set x sub s for all s of size r, which are subsets of the m coordinates. And the x sub s monomial is the most natural interpretation. You just take the product of all coordinates in s, and that's the monomial. So we also need one more notation. So for a point z in f2 to the m, we are going to denote by z to the r just its degree r evaluation, which means that you just take the point z and evaluate it at all possible monomials of degree at most r. So you'll get an m choose less than equal to r long monomial, sorry, long vector. And EMR is just a matrix whose rows are indexed by these monomials that we just talked about, and columns are indexed by uh, evaluation points in f2 to the m. And how do you get an entry of EMR? Well, it's the most natural thing. At a particular monomial which is denoted by s and at an evaluation point z, you just evaluate the monomial x sub s at z. So just hold on, I also have a nice picture to show. So this is what pictorially we are saying, the parity check matrix for the Reed-Muller code that we talked about. Sorry, this should have been -1 over here, but it's, so this should have been -1. I think I made a typo there, but what we really need is the matrix here. So the columns are indexed by evaluation points in f2 to the m. The rows are indexed by monomials of degree at most r, and at a particular row and a particular evaluation point, we just evaluate x sub s at z as we were talking about, and this entire column of the matrix which corresponds to the evaluation point z is what we are calling c to the r. And of course, if we hit the parity check matrix with an encoding of p, we will get the all zeros vector. Now let's see how the BEC channel actually disturbs this picture. So what does the BEC-Q channel do? It erases each coordinate with probability q, right? It just puts a question mark there. And let's suppose that when this encoding of p was sent through a BEC channel, some k coordinates got erased, and let's denote that random set by s, right? You expect that size to be roughly q times 2 power m. And in the diagram, it's the lime colored rectangle which denotes the erased coordinates. They need not be contiguous, this is just for ease of drawing. So what we want to do is recover the information on the erased coordinates, so we get the full code word and hence the message. Of course, this is possible only when k is less than m choose less than equal to r. This is sort of the information theoretic limit. If you erase more than these coordinates, then you don't have enough information to recover the message. So sort of the capacity notion for the BEC channel becomes when you are erasing just shy of m choose less than equal to r coordinates. So we should really be working with the setting when k is 1 minus epsilon times m choose less than equal to r. So with that view in mind, we can now draw the connection with our question and the capacity question. So if we highlight the set of columns which correspond to the set of coordinates which were erased, we realize that what we really want is that this submatrix which is being highlighted in lime over here is full rank, because if it is full rank we can just invert this system of equations and figure out what the missing coordinates were, right? If they are not full rank, if these set of columns are not full rank, then we will not be able to do it. By full rank here I mean that they should have full column rank, right? And of course the dimension of the length of the rows in this submatrix is m choose less than equal to r. So but since the column rank and row rank are the same, this is where we draw our connection. That is, another way of saying that these set of columns are linearly independent is just by asking what is the space of all degree r polynomials which vanish at these k points. They are linearly independent if and only if the space has dimension m choose less than equal to r minus k. Pardon, this square bracket m should not have been square brackets, it should just have been m choose less than equal to r. But the reason for this is simply because column rank equals row rank, and the way to construct a polynomial which vanishes over these k locations is to just take a linear combination of the rows and hope to obtain the all zeros vector when you restrict it to this s columns. So that directly shows that the dimension of such linear combination of rows is going to be m choose less than equal to r, which is the number of variables we have, minus the row rank, which is the column rank, which is k. Okay. So I hope this connection is clear. But moving on to the proof sketch now. So we return back to our original question we asked. So we are just going to, for notational convenience, set u to be m choose less than equal to r, and recall that we are erasing k points which are very close to m choose less than equal to r, like just epsilon shy of it. And we are also going to set the probability that the dimension of IRS, which is the space of polynomials which vanish at s, is u minus k, which is the lowest it could be. This probability we are going to set to p, and what we really want to show is p is 1 minus little o 1, that is p is very close to 1. And what we will instead show is that if you look at the expected fractional size of IRS in the ambient space 2 power in the ambient space of all degree r polynomials which are size 2 power u, then this is very close to 2 power minus k times 1 plus little o1. Well, why this 2 power minus k? Because this is what you would expect, right? Like if this were the event which was happening most of the time, you would expect the size of IRS to be 2 power u minus k, and hence its fractional size is 2 power minus k. What we show is that on expectation this quantity is indeed very close to 2 power minus k, right? And this is sufficient to show that this probability is 1 minus little o1. This is just some very simple calculation which we can follow. So it's based on the observation that if you try to calculate what this expectation is in terms of p, you realize that with probability p, this random variable is 2 power minus k, and with the remaining probability, this random variable has to be at least twice 2 power minus k. Why? Because after all, IRS is a vector space, so if its dimension is not u minus k, it is u minus k plus 1, and hence its size grows by a factor 2, which gives us this expression here. And now if you just sort of manipulate it a little bit, you realize that to have the above quantity to be true, you need p to be very close to 1, right? So now that we've decided to work with this proxy, let's see how the proof goes. So here we are going to now choose q to be a uniformly random polynomial chosen from RMMR, so space of degree r polynomials, and then we are just going to lend ourselves to the magic of conditional expectations and linearity of expectation. So So one way to measure the fractional size of this space IRS is to throw a random polynomial q from this 2 power u possible polynomials and ask whether q is in IRS, right? I mean, that is going to exactly give you the fractional size. But since s and q are independent, we can do this magical swap of expectations, and we can say that well, I could have chosen this random polynomial q in the beginning, and then I could have thrown this k random points, and I could ask whether q belongs to IRS. But that is the same as asking whether these k random points that I have chosen, they all lie in the zeros of the polynomial q, right? So because of this interpretation, we can now start to enumerate over all possible polynomials in RMMR. So let's go over all possible polynomials in RMMR. Say we choose a polynomial p. Then firstly, what is the probability that we actually choose it as a value for q? Well, that's 2 power minus u, because q was being chosen uniformly at random from RMMR. And what is the chance that, given we've chosen p, the k points that you're going to choose at random all happen to lie in the zero set of p? Because this is exactly when p will belong to a polynomial which vanishes, will belong to the space of polynomials which vanish at all points in S, right? So this is roughly going to be 1 minus weight p, because where weight p is just the fractional weight of p, it's the number of ones in the encoding of p divided by 2 power m. So it's going to be 1 minus weight p to the power 1 minus epsilon times u, because remember k was 1 minus epsilon times u, so we are throwing these many random points, and we need all of them to lie in the zero set of p, right? So why is this only approximately equal to and not actually equal to? Well, that is because we were throwing k random points which were distinct in the question. Here if you are throwing them IID, they may not be distinct, and this sort of subtle difference starts to play a role as you try to push r closer and closer to m by 2. For us, it won't play a major role, so we can think of these k points just as IID throws. And now we just sort of manipulate this expression to look like this. So it looks like 2 power minus k times 2 power minus epsilon u and 1 minus weight p to the power 1 minus epsilon u. And what we want to show is this expression is 1 plus little o1 to complete the proof. So let's see how we show that. So this was the expression. We break it up into two parts. So we will, to this expression, we'll try to bound the contribution of high weight polynomials. So polynomials of weight at least half minus delta for some value of delta which is very small. Specifically, delta is set to 1 over u square. And we will try to bound the contribution from those polynomials whose weight is sort of a little away from half, so smaller than half minus delta. And actually the first term is easy to bound simply because the contribution from this exponential term is very low when the weight of p is large. So the larger the weight of p is, the smaller the contribution from this exponential factor is. So a very simple calculation shows that even if you assume the entire space of polynomials belongs to this set, the contribution can only be 1 plus little o1. What's challenging is to bound the other term, because here the contribution from this 1 minus weight p to the 1 minus epsilon u factor starts to matter, and we have to rely on the fact that there are not too many low weight polynomials in the family RMMR. So it's a weight distribution bound, which is what we need, and we use an off-the-shelf bound in the work of Sperlo and Spielka. And that is used to say that although the contribution from such a polynomial is significant, the number of such polynomials is pretty small. And we need to again be careful. We need to divide the weight range from 0 to half minus delta into geometric intervals to carefully absorb this exponential amplification. But after doing all this muscle flexing, we are able to get 2 power minus k into 1 plus little o1. which is what we set out to get. So in conclusion, what we showed is that vanishing spaces of random sets have the maximum possible reduction in dimension or the minimum possible dimension with high probability. And here are some unchecked boxes which we would like to check. One is that we would like to extend this approach to work for R beyond gamma m, beyond there was some small constant gamma up till which we were able to push R by m to b. We would like to get closer to m by 2 plus, in fact we would like to get as close as m by 2 plus minus square root m, which is the constant regime, and sort of give a unifying proof for a large range of parameters. It's already known that you achieve capacity at this regime because the famous results of Kudeker et al. However, we would like to get a unifying approach as well, like the approaches currently in the low rate, high rate, and the constant rate regime for Reed-Muller codes are kind of different. And another very interesting question is that we show that if some expression involving the weight distribution of the dual code is small, then BEC capacity of a code is achieved. What about the other direction? That is, if I tell you the BEC capacity for a particular code is achieved, can you show that this weight distribution that we were alluding to in previous slides, that is actually small? And there is a result of such sort by Samronitsky. But as far as I know, that parameter range is different from the parameter range we are considering. Thank you for your time.